This video is supplemental for our class, and we'll start talking about some of the concepts of classical test theory and reliability. Reliability is a measure of consistency or reproducibility. So we would expect if we have the same individuals in the same circumstance somehow and repeat something over a long period of time, we should expect the same results. This is consistency over many administrations. So we don't ever expect we'll see perfect reliability, but we're going to expect evidence for reliability. We're going to expect measures to be reasonably internally consistent and replicable over time. I thought this was an interesting depiction of reliability and validity. The far left, we see reliable and not valid. We see that there's a cluster of shots, I guess, or arrows that have been stuck into this bullseye, but they're not on target. So reliable means replicable, consistent, but not valid means off target. And I'll talk more about validity in a moment. Low validity and low reliability, we can see that second target is missed quite often and in random scatter. So we have neither reliability or validity, or at least it's low. And then not reliable and not valid, the third one, we see that there's really the reliability is both scattered and the validity, well, we're not even centered around that target. It's actually missing the target. So validity, we spoke about earlier in the semester a bit, and maybe one of the things we talked about is that are we representing what we think we're representing, and in this case, maybe our target is off center. Both reliable and valid means that we're going to be able to replicate something, and that measurement that we're replicating over time is what we think it is. And we'll talk more again in class about reliability and validity. We'll also use the standards of education and psychological testing and actually talk more appropriately about evidence for reliability and evidence for validity. Errors of measurement can be both systematic and random. Systematic due to the characteristics of a person or the test. They reduce accuracy but not consistency, and they persist across measurements. Whereas random error of measurement is a chance happening. It reduces accuracy and consistency. They can be positive or negative. One might think of this as something guessing. It could be a distraction. We have so it could be some scoring error, and we can think of these types of error from a measurement model perspective. When we look at systematic error, this might be a grouping effect, a treatment effect, some sort of systematic process that's not really, we're not going to talk about it further as error, but random error is kind of that random fluctuation that occurs. Systematic error or systematic bias might be easier to identify and remove, whereas random error we have to learn to deal with, and we'll see how we do so in classical test theory. As an example, just a silly one here, maybe a systematic error is occurring in this picture. I'll let you decide if that's funny or not. Classical test theory. We can think of this sometimes called weak true score theory or classical true score theory. It's a way for developing estimates of systematic variation and random error for a given set of test scores. We are looking for true scores, true values, and we'll see how we go about trying to construct these. But one of the really cool things about classical test theory is it's very practical relatively straightforward, easy method to learn and easy to study reliability, which through an empirical process. We're going to see that it's tied to a given sample, which means that all of the assumptions we make about other research, about the quality of our research given our sample is still true, and that there's not going to be as many strong assumptions as we'll see later on, maybe when dealing with item response theory. Random variables. When I think of random variables, it's easy to think of dice. Maybe we have a pair of dice, we're rolling dice, and we can come up with true probabilities. That is, we could map out the number of times snake eyes, 1-1, or a pair of sixes, double sixes would roll, how many combinations there are of fours and fives, or even if we wanted to sum, so how many twos, threes, fours through 12s are there, and we would find that 7 is the most probable based on theoretical probabilities, but empirically, well, empirically, we could get any roll of the dice on any single die roll. So we could test the dice and get estimates over many, many periods of time instead of just relying on the theoretical probabilities. You might think, well, what's the difference? It is possible that dice don't land perfectly and evenly on the side they're supposed to, and that they could even be biased. We could test for that. So we could, in theory, do this over, well, in theory, we could do it over an infinite number of times. But we're going to see where we look at this as an expected value, which will have symbols as seen below. And our expected values are going to be things we might think of when we relate back to the mean and central tendency. We could at least go back 100 years or so to Spearman to see some of the foundations of classical test theory. I'm going to go ahead and talk a little bit about some of the model. So we could suppose, for instance, that we have persons n, which are from 1, 2 through capital N. So person 1 to n. And if we could test them in each person's infinite number of times without any change, maybe somehow erasing memory, we could go through and try and get a score about that individual, uh, assuming there was no change due to learning or maturation. And this is the premise of classical test theory. Well, one of the two premises, one of the two ways of looking at least the classical test theory. We'll see in our text later on that there's two ways of looking at it. So we can look at persons from n to n equals 1 to n, but we also want to throw in this subscript of I. This could be assessment or item. We'll look more at these later. So our values here, we see x sub ni, so x for any given person or any given assessment is equal to t, which is a true score, plus error. So an observed score, what we observe, is equal to some amount of error and some amount of truth. So we can relate those concepts back to our systematic variation and that random error fluctuation. And this is the premise behind classical test theory. So just more formally defined here for you, classical test theory, that x sub ni is the nth person's observed test score and the ith administration. The true score is the nth person's true score in a test, so each person has their own true score. And then they have error, this e sub ni, this is the error in the person's observed test on the ith administration. So you may have a true score, and then these errors may cause the observed score to fluctuate. As we start thinking about true scores, we can start to think about these concepts we thought earlier about in the semester already, about constructs and latent variables. We may have all these ideas we put together and build constructs based on what the observed phenomenon is, but really what we're interested in is the underlying ideas and constructs that these manifest variables indicate. So all of those variables may end up indicating something about human cognition or intelligence or something unseen, another psychological measure, and we can see that what we see when we build as a construct is reflected somehow also and what the truth really is. So as we come up with all of these pictures from um, our manifest variables, we might come up with something pretty good, but it might not be true. It's just kind of a reflection of truth. For those of you more interested in this, we'll talk a little bit more about it in factor analysis later in the semester when we do just our brief introduction to factor analysis. And really, this is a fascinating topic for you if you go into more structural modeling, like structural equation modeling, or maybe latent class analysis. So we've got this model. X sub ni, observed score, is equal to some truth plus some error. So true score, test score, is going to be equal to your true score plus some random fluctuation. True score is the average of an individual's observed score over an infinite number of replications. That's one of the ways we can define true score. So our mean, our average of all of ours, so we see here mu is the summation of all of our scores divided by n. Mu is also, we can think about our scores times the probability, proportion correct. We talked already about some p-values this semester. And our true score is also, we can see, equal to what's called the expected value for our observed value, which is equal to the mean of those observed values. Error, on the other hand, is equal to the difference between observed x minus t, true. And we can think about this in statistical test theory, is that with the expectation of error, that means the average score of error, if we summed up all the errors and divide by the number of instances, is going to be equal to the expectation of the observed scores minus the expectation of true scores. So the expectation of error can then be the next step down, as we have is equal to the expectation of our observed scores minus true score, because the expectation of true score is just true score. And then we see that our expectation of error, well, expectation of observed score is actually true score, and our true score is true score. So the expectation of our errors over time is 0. All of that means that as we go through time, we expect on average that errors are going to balance out on either side of our true score. So you make one error, you make 2 errors, you make 3 errors, you make a whole bunch of errors. They're all surrounding the true score. So they'll fluctuate. Sometimes you'll have a score that's a little bit higher, and sometimes you'll have a score that's a little bit lower. And here we have the dull. Sometimes we think of errors as only negative, but we can have a error that is in a positive direction. That is, you end up with a score higher than what your true score is. There's a couple of the definitional properties of true and error scores you should be reviewing in your text. The mean of error scores for population is 0. So mu, j equals the expectation of 0, which equals 0. We have the correlations between true scores and error scores for population of examinees is 0, so there's no correlation between those two things. And the correlation between error scores on 2 different tests, assuming independence, to be 0 in the population, so no correlation there as well. Here we have an example from our textbook, and we are, not we, but Crocker and Algina plotted 2 sets of plots for a large group of examinees with a 10-item test. And we have, on the top plot, we have selected true scores, and we see what error is. We have the values of plus or minus 10, centered at 0. So on average, there's 0 error. And we can see that we sort of have that x's, the means of score groups going across that middle there at 0, and we see some fluctuation around on either side. On the bottom plot, we see random scatter. And this is because there's really no relationship to be found. I mean, you might be able to divine some sort of picture in there, but there's no intended correlation drawn in this or demonstrated in this plot. So this is to show that in any instance where their true score value is correlated to the error scores. Parallel tests are meaningful, in particular, and practical, in particular when we get into testing situations. So what we would like to have in an ideal world are parallel tests that have the same true score and the same error variance. So that means if you take either test, it doesn't matter. You would have reported the same true score for an individual and the same error variance around those true scores. This often doesn't happen, but it's our ideal. So parallel tests, you might think, I sort of have this silly parallel universe set up here where everything is replicated over time and or place, and our tests would be effectively identical, which would be great for equating purposes. It is more likely, but not necessarily likely, that we have what's called tau equivalent tests. So these have the same score, same true score, but the error variance have a different band. So the error variance for one may be different for the error variance for two, but the true scores are the same, which is pretty strong actually, that our true scores would be the same. And again, even a more likely scenario is that the true scores have something in common, but they're different by a constant. And also our differences in our error variances. So when we have different bands of error, and the true score may be different for each test, but by being different by a constant, it makes equating relatively easy. And I just say relatively, not that it's easy, it's just relatively easy if this were to actually hold. A further type of, I won't call it really parallel at this point, but further type of comparable testing is when our true scores are different by a linear function and there's a difference in error. So we call these congeneric tests. So we have a true score for test 1 plus some error, and then we have that same true score, but we have it being different by a linear function. So we could be multiplying, dividing, adding or subtracting a constant from that true score. Then we have another error with a different error variance. When we think about the reliability of a test, we can think of the proportion of observed score variance. That is true score variance. So kind of think of true score over observed score. Maybe even this relates back to your analysis of variance or regression courses. I have here some of the simplification from the book just to talk about some of these relationships. We talk about the relationship between observed scores and true scores. If we really could observe true scores, we could talk about that correlation. But really what happens is we can observe scores on a test 1, maybe x1, and test 2, x2, and we see through some of our transformations here that we get the variance of true scores over the variance of observed scores. And if you took the square root of that, you would effectively get the standard deviation of true score over the standard deviation of x. You can sort of look a little bit more for the proof in your textbook, and we'll talk, or can talk, a little bit more about this in class. But this is one of the this is one way of looking at the reliability index. And again, this is the degree of relation between a true score and an observed score. So we can basically take two tests, get their correlation, get some estimate of what the relationship of observed score to true score should be. We also consider the reliability of a composite. You should become familiar with the Spearman-Brown formula. We can imagine that we have k parallel tests. So we have C equals A plus B all the way through K. And we can kind of decompose this into observed score variances and covariances. And we see down bottom that the variance of our composite is equal to the variance of A plus the variance of B plus all of the individual variances all the way through K, plus that summation of uh, the correlation times the standard deviations is effectively our covariances. We do that for all possible covariances. So it's the summation of all of our variances and covariances. So in certain cases, things simplify. We can have parallel variances. So our variance composite now is just k times the variances plus k times k minus 1 times the correlation times the variances. And then if we have our correlation is set to 1, this simplifies even further that our variance of our true scores as a composite is equal to k squared times the variance. So the Spearman-Brown formula takes these two equations. The numerator is the k squared, variance squared, times the variance squared, and the denominator is the k times our variances plus k times k minus 1 times the correlation multiplied by those variances. So the Spearman-Brown formula and coefficient Cronbach's alpha we're going to practice in class are related conceptually. Cronbach's alpha may be the most famous reliability coefficient, is again related to this idea of a composite and that we have k parallel tests, and we're going to think about the reliability of the composite being true score over observed score variance. So we have true score variance over observed score variance, and we can see that this is actually set up as inequality. And maybe for the proof of the inequality, one could go back and read a very famous text, Lord and Novick, and sort of deconstruct the proof for you. But here we're just going to talk a little bit about the relationship of the class, and that this becomes the reliability is sort of a lower bound of reliability. So alpha, we can think of this compared to the Spearman-Brown formula, Spearman-Brown approach, which is going to be a split half approach we'll test out in SPSS during class. But we can think about alpha is going to be the average of every possible split half. So for a split half test, which is really, again, that Spearman test, you basically take the test, split it in half, find the correlation between the two halves, and that's an estimate of reliability. But how you split the test matters. But for alpha, we do every possible, get an average of every possible split half, so the average doesn't matter. So the difference in the split doesn't matter. So Cronbach's alpha is equal to the reliability of this composite test when it's, we look at parallel tests and tau equivalent that we talked about before, but it's really I mentioned the lower bound for reliability of the composite tests in pretty much all other cases. If you have essentially tau equivalent, or you have beyond essentially tau equivalent, we have what we like to see large values of reliability, usually a value thrown out as a minimum that we're searching for is about a reliability of 0.8. More discussion on that later. It really depends is the answer to what your reliability should be. And again, you will find that if you stay in the field of psychometrics or assessment, educational assessment, that this is really just one measure of reliability and one indicator, one piece of evidence for reliability, and there are other measures as well. So in some of our earlier talk, we talked a little bit or hinted a little bit around the standard error of measurement. And especially when we talk about standard deviations and regression models, the very simple regression models you probably learned in the introductory stats course, that we have some sort of fluctuation around the scores we observed, and we can sort of think about the standard error of measurement as a way of taking a peek at individuals, uh, an individual's score, observed score, how much variance there would be about their true score. So we expect there to be variation on people's scores that are observed, and that's different than those true scores. We can sort of set this up the same way we did with our observed score for classical test theory of x is equal t plus error. Now we have the variance of x equals the variance of t plus the variance of error. So we could just divide everything by the variance of x here. We see that we have first, we have a ratio of the variance of x over the variance of x, which obviously is 1. Then we have the variance of t over the variance of x. And we saw earlier where this was a reliability measure. We correlated two test scores. Well, let's pull this off to the side and see what we have. Well, we have 1 equals the reliability plus this ratio of error over observed, or the variances of error over variance of observed. So we can just pull the reliability over to the left-hand side of the equation. So we have 1 minus this reliability equals this ratio of variance of error over the variance of x observed. And if we take and multiply both sides by the variance of x observed, and then take the square root, we get the following equation, which is the standard deviation of x times the following under the square root, 1 minus reliability equals the variance of error or the standard error of measurement. And that's how one way we can think of the standard error of measurement is that it's 1 minus the reliability. So if we have reliability, 1 minus all of that, we can take the square root of and multiply by the observed score or standard deviation. So just a couple comments here. The root of the average value of error variance across all examinee test scores is the standard error of measurement. We can think of the standard deviation of an observed score given a true score, and the standard deviation of one person's observed score across an infinite number of test replications. So this is a little bit of information for you that we'll follow up with in class, but and with your readings on the standard error of measurement in your text. We'll go through some procedures for estimating reliability. One of the easiest ways is if we could just correlate two tests. It's not exact, but it's an estimate, and we could get this by calculating it from sample. So we'll start off with some of the basics with alternate forms and test-retest situations and the correlations amongst those. In alternate forms, we could think about parallel forms, different methods. We could administer two forms to the same examinees and correlate the tests. This correlation would be the reliability coefficient, and we call this the coefficient of equivalency. Between the two forms, if we get a correlation or reliability of about 0.8, we consider this pretty good. So just pictorially, I just take two forms and I'm drawing that correlation. Test-retest is a situation where we have the same form at two different points of time. So we may administer them to the same examinees at alternate points in time, and then we could correlate the scores from the two tests and get what we call the coefficient of stability. This sort of assumes no change in their true score over time, which if they're exactly the same test, there could be a lot of suspicion here whether there's change just by having taken the test. But if there's long enough time, we might suspect that maybe memories fade, whereas maybe in short periods of time people could recall some of this. So you have to balance out the amount of time for test retest. If someone knows they're getting the exact same test again, this could also influence the score. All this will depend on what construct you're actually measuring, how much time should be involved, and point 8 is preferred, but often if you really get a test-retest situation, then maybe point 7 is an okay measure here. But again, for any reliability you ever report evidence for reliability, whether it's one piece of evidence or 100 pieces of evidence, I would have well documented the rationale for a threshold for what I consider good. This could be coming from, secondary sources like our text, but you should go to primary sources in journals that we point toward in class. So if we have a test at time 1, and then we have a test at time 2, we can get the correlation between those two things to get our coefficient of stability. We could also, and often, have a situation where we just have one test. There's several things we can do here. There's different split half measures. You'll see most popular, the Guttman measure, Spearman measure, etc. They're not very popular. I mean, they're still done, but they're not popular relative to Cronbach's alpha and the associated measures of KR20 and KR21. So, and also Hoyts-Nova, which may be some of the foundational thinking when we get into Cronbach's later measures that he worked on with other folks for generalizability theory. So we just take two portions of the test, as you just saw my test kind of split in half. That'd be split half reliability, and if we took every possible iteration of all possible split halves, we get Cronbach's alpha. Just a nice little neat graphic for you to show you that we're splitting two halves. So I have sampled from our textbook, I think what is a nice summary, still a very effective summary of these ideas and approaches to reliability, 3 different approaches. We have changes over time, this coefficient of stability, and we can compute a Pearson product moment correlation coefficient. We have content sampling from form to form, the equivalence, the coefficient of equivalency, and we can again compute the Pearson product moment correlation coefficient. And then we have measures of stability where we're going to look at the Spearman-Brown split half formula, Guttman's formula, but also we'll end up looking at Cronbach's alpha, or alpha. Sometimes I think it's been mentioned by Cronbach that he wishes we hadn't called it Cronbach's alpha, because that's not quite what he called it. Iterator reliability is another form of reliability where we may have multiple observations from for an individual by multiple raters. I have 2 raters, but it could be more than 2. We could do a Cohen's kappa. Generalizability theory helps with inter-rater reliability, but the general concept here is often you have situations of maybe performance or complex assessments that require a human rater, some sort of evaluation of judgment. And in that case, we would like to see how correlated our judgments are. Sometimes we might even talk more about the rater's reliability with oneself. Factors that affect reliability are group homogeneity, how similar the groups are, the time, if you have any time limits could impact reliability. Shutting off a test early could cause a lot of non-responses. Test length can impact reliability. A classical statement in classical test theory is that the longer the test, the more reliable. And we can also have extreme items and responses that can impact reliability. Our true score estimates can be generated. We tend to have observed scores above the mean, overestimate true scores, and observed scores below the mean, underestimate them. So it's kind of like sort of a regression back toward the mean effect here, in that we end up having values, individuals will be end up closer to the group mean for their true score than their observed score. We almost never have a correlation of 1. That would be actually new, sort of the true score, but we usually have that reliability component, which is the last 0.8, 0.9. So we're taking the difference between their score an individual score minus the mean times their reliability component, and then adding the mean again. And that will effectively be one way to get us our true scores. A use of a true score sometimes is used in norm referencing. It doesn't really have much impact if you do that, and basically because the rank in the population will remain the same. But you have to be careful in criterion testing, that it could have an impact because of the way it regresses back toward the mean. So individual, because an individual is being compared to a threshold. So for norm reference, we're comparing everyone to each other, so everyone is kind of equally, or at least rank orderly, proportionately brought back toward the mean. Whereas in a mastery assessment test, that cut-hold and threshold of success matters. So there will certainly be occasions where maybe different scores matter. And here we'll just talk about some of the conceptual issues, but here's an equation that we have to be able to derive the correlation to reliability component of our different scores. So the largest reliability will occur when the reliability of the pretest and post-test are high, but the correlation is low. So if we have a variance, or I'm sorry, standard deviation of 1, we can sort of reduce this equation down, reduce its complexity down a little bit, and what we end up seeing is that it's only positive when average reliability of scores of x and y is greater than the correlation of scores of x and y. So this is where maybe some problems arise in classical test theory, at least one of the places. And there'll be researchers who say that this is a problem because we want tests to be both reliable and correlated to each other. So some researchers say that test theory breaks down here. Others just suggest that maybe this is just an artifact of the way the definition of classical, reliability. So there's some debate out here. There's certainly the suggested, using measures that have the suggestion would be to use measures that have small error variances and large positive correlations when possible. Really, we really do want those tests to be both reliable and valid. We can also have our error estimate of a true score, standard error of a true score. We have to be careful with the interpretation here, not to make sure not to confuse this with the standard error measurement. So notice that we have under the square root 1 minus that reliability squared. So using true scores instead of observed scores again, if we've done this, we have to be careful depending on whether we're using norm or criterion referencing. But if you do, then we can look at that second equation there as a error estimate for true scores. I'll just mention a couple things about reporting reliability from your textbook and maybe match it up to the current thinking in the standards of education psychological testing. Talk more about this in class. Obviously, one of you will be doing a report for us. But, we think now, we talk about reliability as evidence for reliability. So if you have different sources, report them. Different studies have been conducted, report different values. It's okay. For our standard error of measurement, we may have some score bands with confidence intervals. This may be helpful in reporting. Report subtests. So if you have 3 subtests, you can report the reliability of subtests. It's okay if those subtests are low. It's evidence for those subtests. So evidence of reliability in those subtests. And then make sure all your procedures are transparent. Don't hide anything. This is true of all of science. and all of statistics. Just be transparent, have a clear method, and let people know how you did things. And then, well, the last thing I'll say about this list really is if you have a specialized population of interest, you may want to focus on them as well.